In this video, we will go through some properties of unitary matrix and how it is related to single qubit quantum gates, and we will write some simple programs using Python and NumPy. So let's recap. So a qubit can be represented by alpha 0 times state 0 plus alpha 1 times state 1, where alpha 0 and alpha 1 are complex numbers and the square of the magnitude to be added to equal to 1. And in the previous video, we also talked about unitary matrix. Unitary means that the transformation on a qubit preserves the inner product and is reversible. And in this video, we will introduce another representation for qubits. It is the vector representation, so that we can focus on the change in probability or magnitude change for different states. And for state 0, it can represent by a column vector 1, 0, and state 1 can be represented by another column vector 0, 1. Since unitary matrix is an important part to form a quantum operation, so it may be better for us to write some program to check whether a matrix M is a unitary matrix. That is, we want to find out whether M multiplied by M dagger equal to an identity matrix. So we can write a unitary matrix tracker in something like this in Python. So basically, the first line is a definition of this unitary function, and the first line in the function is M dagger. That is, in NumPy we can use the get H function to get the conjugate gate transpose of M. And then we can compare the dot product of M and M dagger with the identity matrix. In NumPy, it is generated by using the function np.i. Due to some numerical error, we need to use np.allClose to check whether they are very close, that is, whether they are equal. Let's try to use the function on some matrices. For example, 0, 1, 1, 0, this matrix can be defined using NumPy using the np.matrix. And then we can use this unitary X to check whether it's unitary or not. The returned result is true. Another matrix which involves an imaginary part, we can define using np.exp compass 0, 0.25 to define the imaginary entry. And this matrix is also a unitary matrix. Lastly, we can define another matrix using the compass function. And for this matrix, it is not unitary. You may try to compute by hand to check the result. So actually, there is a general expression for the 2x2 unitary matrix. There is something like that. And there is a condition for A and B, that is A squared plus B squared equal to 1. And there are 4 parameters in the expression. The first one is the phase alpha, and another phase beta, and a phase offset theta, and the relative magnitude between A and B. Given the expression, we can define a Python function to basically define the parameters alpha, beta, theta, A, and B to generate a unitary matrix. So a program is shown here. Basically, the line search means that I want to check whether the condition alpha squared plus b squared equal to 1, and the remaining 5 lines are about setting up the unitary matrix U based on the expression. For example, we can define alpha, beta, and theta as 0, A equal to 1, B equal to the square root of 1 minus A square, and then we fit these 5 parameters into the unitary matrix function to obtain a matrix M. Then we can track whether it is unitary or not. And because it is based on the expression, therefore it should always be true. However, if we set b equal to 1, then when we run the program, we see the assertion error. We can see that the error message said that the line 2 assert np.all np.square a plus np.square b, comma 1 is false, because 1 square plus 1 square equal to 2, not equal to 1. Given the expression for the unitary matrix, we can write a for loop function to generate many of unitary matrices. Given this program, we can generate a set of matrices as shown on the right. And we can see that there are many possible matrices with different values of A. So some of these matrices are more special than the others, and a kind of them is called the single qubit gate, which is a quantum logic gate that forms the basic unit of quantum circuit. And usually a single qubit gate only operates a small number of qubits, say 2 to 3 qubits. And in general, given a qubit alpha 0 and alpha 1, we go through a single qubit gate G1 and produce a change in magnitude, that is alpha pi 0 and alpha pi 1. And in this video, we will go through 4 single qubit gates. Why these gates are more important? Because some of them is meaningful in physics, some of them is more easy to understand by beginners, and some are useful building blocks in some famous quantum algorithms. Not to mention that some of the qubit gates are built in the quantum computer. That means that using those gates, you have a shorter running. The first one is the Bitflip gate, also called the NOT gate. It is represented schematically by X. And what it does is basically to convert 0 to 1 and 1 to 0 when we apply X on the state. And if we use the vector expression, we can see that the magnitude probability of stage 0 and stage 1 flips. And if we write X in matrix form, it will become this unitary matrix 0, 1, 1, 0. For Phaseflip Gate R05, the schematic diagram is R05. And the function of the Phaseflip Gate is to keep state 0 intact, while stage 1 we will multiply a phase on it, that is EI5. And when we look at the magnitude or probability change, the phase of stage 1 is shifted. However, the probability of finding stage 1 is not changed because the square of EI5 is 1. And the operator R5 can be represented using this unitary matrix. And there is a special case, Z, which is R. And Z is a Phaseflip gate. The Phaseflip gate, because it is a R5 gate, therefore the stage 0 remains intact. The phase of stage 1 is shifted by pi, meaning that 1 changes to -1. Stage 1 will be phase flipped. When we consider the magnitude of stage 0 and stage 1, we can see that the magnitude of stage 1 is the negative of the original one. And when we look at the matrix operation of Z, it will become 1, 0, 0, -1, which is equal to 1, 0, 0 e to the I pi. Lastly is the Hadamard gate. Hadamard gate is very important in developing quantum algorithm. And the function of Hadamard gate is basically to split magnitude of the state into two parts, which means that a measurement will have equal probabilities to become 1 or 0. And when we apply H to a quantum bit, we can see the computation will become something like that. Hadamard gate has on alpha 0, alpha 1, that becomes 1 over square root 2 alpha 0 plus alpha 1 alpha 0 minus alpha 1. H can be expressed in this matrix form. The Hadamard gate is the 1-qubit version of the quantum Fourier transform. According to some research paper, Hadamard gate is all that one needs to add to classical computations in order to achieve the full quantum computation power. Therefore, in the subsequent lectures, you will often see Hadamard gates.